check the check the which target state. What is the target state, and whether the guard condition is satisfied. So the guard condition is usually a Boolean expression, and it must be true in order for a transition to occur. It means that if the Boolean expression does not satisfy, the transition fails. And a guard transition fails when its event occurs and the guard condition is true. That's what we have explained. It means only when the events occur and the guard condition is true, the guard transition can be fed. And a guard condition is only checked once at each occur of the event. It means that whenever it gets the guard condition is placed following the event, but the guard condition will not be checked continuously, and it is only checked once at each occur. It means of the event. It means whenever the event is failed, the guard condition will be checked, and only when the guard condition only then the value of the guard condition is true, this transition is success. Otherwise, this transition will fail. This is an example for the guard conditions. And this is a state diagram for a software to controlling the traffic lights at an intersection, and this is the north, and this is the west, and this is the turn left lane, and this is the go straight lane, the straight lane. This is a turn left lane, this is a turn left lane, this is a straight lane, and we assume that at first it exists northwest, north-south goes straight, north-south goes straight. It means this car is running. And timeout is an event. For example, 30 seconds. After 30 seconds, the timeout is an event. This state receives an event timeout. And guard conditions are parenthesized in the brackets. Cars in north-south left lane, north-south left lane. It means if there are cars in the north-south left lane, this transition fails. It means only when it gets the event timeout and this condition satisfies, this transition fails. And if it gets the timeout, the event timeout, but this guard condition, the value of this guard condition is false and the value of this guard condition is true, this transition will fail. It means the source state will transfer to different target states according to guard conditions. Okay, let's see that if here we can see that here are cars in north-left lane, then it will go to north-south may turn left. It will go to this state, turn left state. And in turn left state after 30 seconds, we get another timeout event. Then it will go to east-west go straight state directly because there is no guard conditions. But here, in the east-west go straight, it will check whether there are cars in the east-west turn left lane. If there are turn left cars in the east-west left lane, it will transition. It will transition from this state to this state. It means go to the east-west turn left state. And then, when at this state, we get another event timeout, it will go to the north-south go straight directly. Okay, we can see that. In this traffic management system, we need to check whether there are cars in the left lane. So we need some electric eyes installed to check the north-south left lane and the east-west left turn lanes. Okay, maybe we can call it an AI-enabled traffic lights. Okay, state diagram. Just now we have introduced about all the main items or main elements of the state diagram. It is the state, events and transitions, guard conditions, and now we can build some state diagrams. A state diagram is a graph whose nodes are states and whose directed arcs are transitions between states. And a state diagram specifies the state sequence caused by event sequence. And a state diagram models the common behavior of objects of the class. It means we will model the common behavior for the same class. And the state model consists of multiple state diagrams. One state diagram for each class. It means for each graph, for each diagram, it is only for one class. If we have multiple classes, then we will need multiple diagrams. And events and guard conditions may appear in a single state diagram or among individual diagrams. And currently, because we have different diagrams for multiple classes, so there may be transitions among different diagrams. Because although different classes are modeling separated, but there are relationships among them, so there may be state transitions among them. Okay, this is a sample of state diagram. This is a state diagram for a telephone line, which concerns a phone line rather than the caller or the callee. It means we focus on the phone line. It contains sequences of states associated with normal calls as well as some abnormal calls. for example, some busy or some timeout and so on. And UML notations for a state diagram is a rectangle with its name in a small polygon tag, a small tag in the upper left corner, and the states and transitions lie within the rectangle, within this rectangle. And states do not totally define all values of an object. It means this is a principle to selecting states. For example, for the dueling state including all sequence of incoming phone numbers. It is not necessary to distinguish them because they have the same behavior. It means at this state dueling, when you are dueling, only when the number dueled is valid, it means it has all the phone number is inputted completely. It means, for example, if a normal phone number is 9 digits, then after you have digit 9 numbers and it is valid, it will go to the connecting state. Otherwise, it will be invalid. So in this state, we don't need to distinguish the numbers dealt. It means we don't care much about the difference about dual number. We only check whether it is valid or invalid. And there may be many phone numbers are valid, and there are also many phone numbers are invalid. But we needn't to care much about in this state whether it is what is the detailed number is. But we need an attribute here to store what is the phone number dual, and then we will check whether it is valid. Okay, we can see from this one, from the idle. At first, the phone line is idle. If someone picks up the phone, it will off-code into the dual tone state. And if after, for example, 20 seconds, no number dual, so it will go to the it get an event timeout, it will go to warning state. In warning state, it will, if it still get, if for example another 20 seconds no response, it will get another event, go to another state timeout, and finally unhook. And if it gets if the number is dueled, and it will go to the dueling state. And if after set 20 seconds, for example, it didn't duel, it doesn't completely input. It doesn't. A complete number is not dueled. For example, if only 7 number is dueled, it is not a complete phone number, and it will be get another message event timeout. It will go to the warning, and in the warning, it will go to unhook. And after 9 numbers are dueled, it will check whether it is a valid number. If invalid, it will go to recorded message. And if it is valid, it will connecting. If the number is busy, it will go to busy tone. And if chunk busy, faster busy tone, if it is rooted, it will go to the ringing state. In the ringing state, if it is unhooked, it will go to idle. If called phone answered, it will go to connected. In the connected, if it is unhooked, it will go to idle. If it is called phone hangs up, it will also go to disconnected. Okay, all of these are messages, are events, and here this is rounded box are states. So this is a complete state diagram for a telephone line. And just now for the telephone line, it is a continuous loop. And sometimes we have one short life cycle. It means there's the states, there's no loop in the states. And one short state diagram represents objects with finite lives and have initial and final states. It is not, there's no loops in the one short state diagram. And the initial state is entered on creation of an object, and entry of the final state implies destruction of the object. Okay, this is an example for the one-shot diagram. This is a simplified life cycle of a chess game with a default initial state, solid circle. Okay, this is the initial state, and then go to white's turn. And after white moves, okay, it get a message, an event white moves. When it get the event white moves, it will go to the state black's turn. In the black's turn, when it gets the event black moves, then it will go to the white's turn. And if checkmate or stalemate, it will go to the final states. And you can also use another type of start and final states. For example, you use a hollow circle represent the entry point, and some circle enclosing on X appear and on the state diagrams parameter and maybe named. This is the exit point. There may be multiple different exit points according to the event, and it is the start. Okay, this is a summary of basic state diagram notations. A box, a tag of the state name, of the state diagram name, and a rounded box is state, and the transitions lines are transitions, and arrows pointed from the source to the target states, and the events, attributes, conditions, and some effect. State is a rounded box. Transition a line, an arrow points to the target. Event is a signal event is shown as a label on a transition, and may be followed by parenthesized attributes. And a change event is shown with the keyword when, followed by a parenthesized Boolean expression. And a time event is shown with the keyword when, followed by a parenthesized expression involving time, or the keyword after. It means that there may be when after, also followed by some expressions and gather conditions. It is optionally listed in a square bracket after an event. This is a gather condition. And effects can be attached to a transition of state. This is an effect of here. This is the effect of the event. It is listed following a slash. And the effect, we will study the effect in the following sections. Okay, this is an access in class. Okay, you can see that this is a partially completed diagram for one kind of motor control that is commonly used in household appliance. A separate appliance control determines when the motor should be on and continuously assigns on as an input to the motor control when the motor should be running. When on is asserted, the motor control should start and run the motor. The motor starts by applying power to both the start and the running winding. A sensor called a starting relay determines when the motor has started, at which point the start winding is turned off, leaving only the run winding powered. Both windings are shut off when on is not asserted. It means we need applying power to both start and run winding to start the motor. And after the motor is started, we need to shut down or turn off the power for the starting start winding and leave the power for the run winding. But if the on is not asserted, both windings are shut off. And appliance motors could be damaged by overheating if they are overloaded or failed to start. To protect against small damage, the motor control often includes an over temperature sensor. It means we have a sensor to test the temperature. If the motor becomes too hot, the motor control removes power from both windings and ignores any on assertion until a reset button is pressed and the motor has cooled off. It means that when the temperature is too hot, the power will be removed from both windings and it will ignore the signal on and until a reset button is pressed. It means whenever it is too hot, the on button will not take effect. And only after a reset button is pressed, it means you need to reset. But if you reset, it will change to the normal state only when the temperature is not too hot. It means that if it is too hot, even if you press the reset button, it will not work. And add the following to the diagram. What do we need to do? We need apply power to run winding, apply power to start winding. We need to add these activities and we need to add events. Motor is overheated, on is asserted, on is no longer asserted, motor is running, reset. This is events and some conditions, motor is not overheated. Okay, activities, currently we haven't studied the activity. Activities means some behavior within the states we need to do within the state. Okay. This is the complete state diagram for this motor control system. We can see that off, starting, running, too hot is the given state. And on is asserted, on is no longer asserted, motor is overheated, motor is running, motor is overheated. These are events given here, events. And motor is not overheated is a condition given here, condition, motor is not overheated. Okay, it means that at first it is at the off state, and when on is asserted, it will, and to go to the state, it will transition from off to starting state. And it will do something. This is called the activity. We will study it in the next time. Next time. And it means apply power to run winding and apply power to start winding. It means that in starting state, we will apply power. And if motor is running, this is monitored by the sensor. And it will go to the running state and it will apply power to run winding. It means that it will shut off the power to the start winding. And here, when it gets the event motor is overheated, it will go to the state too hot. In the too hot, if we press the reset button and the motor is not overheated, the gather condition satisfies, means the value is true, it will go to the state off. And then you can press the button on to restart. But in the starting, if on is no longer asserted, it means when you are starting and you press on again, the on is not asserted, it means it will go to off. And in the starting, if motor is overheated, it will also go to the too hot state. Okay, this is very easy to understand for this state diagram. It is a state diagram for this motor control system for controlling the motors. And usually this kind of knowledge, this kind of logic is implemented using hardwares, but in some it is used to sometimes for some other appliance may use currently may use some chips within softwares to control some appliance. Okay, here are homeworks.